July 5, 1943, Kursk salient, Soviet Union. 200 rebuilt Panther tanks from Panther Regiment von Lauchert, the 39th Panzer Regiment, prepared for their combat debut in what would become the largest tank battle in history. 184 Panthers were operational that morning, representing Germany's newest weapon, a medium tank mounting heavy tank armor and firepower that intelligence reports claimed would revolutionize armored warfare. Within 48 hours, only 40 Panthers remained operational. Within 2 weeks, operational strength collapsed to just 16%. The Panthers' catastrophic debut at Kursk would expose a fundamental contradiction in German tank design that Allied intelligence would spend the next 2 years systematically documenting, a contradiction between impressive specifications and catastrophic mechanical reliability that shaped the outcome of the war. The Panther emerged from Germany's desperate response to the Soviet T-34, a tank that shocked German forces when encountered in summer 1941. The T-34 combined sloped armor, a powerful 76mm gun, wide tracks for mobility, and mechanical simplicity into a design that rendered German Panzer III and Panzer IV tanks obsolete. In response, the German Army Weapons Department issued specifications for a new medium tank in November 1941. The design competition between Maschinenfabrik Augsburg-Nürnberg and Daimler-Benz resulted in Mann's design being selected in May 1942. Production began in January 1943 with the Aust D variant, followed by the Ausf A from August 1943 and the Ausf G from March 1944 through war's end. The specifications were impressive on paper and represented genuine advances in armor design and firepower integration. Combat weight of 45 metric tons placed the Panther between American medium tanks weighing 30 tons and German heavy tanks like the Tiger I, weighing 57 tons. This intermediate weight class was intended to provide heavy tank capabilities with medium tank mobility and production cost. Frontal armor of 80mm, sloped at 55 degrees from vertical provided protection, equivalent to approximately 140mm of vertical armor, through the principle that sloped armor increases effective thickness relative to the projectile impact angle. This sloped armor design, copied from the Soviet T-34, represented a significant advance over earlier German tanks that used vertical armor. Side armor of 40mm provided adequate protection against light anti-tank weapons and autocannon fire, but remained vulnerable to all Allied tank guns and medium anti-tank guns at combat ranges. The main armament, a 75mm Quake 42 L70 gun, represented the most powerful tank-mounted weapon in widespread service during 1943 and 1944. The designation L70 indicates that the barrel length was 70 times the caliber, providing the extended barrel length necessary for high muzzle velocity. Muzzle velocity of 925 meters per second with standard armor-piercing ammunition provided penetration capability exceeding any Allied tank gun through 1944. At 1,000 meters range, the gun could penetrate 120 millimeters of armor, sufficient to defeat any Allied tank frontally. At 2,000 meters, penetration remained adequate to destroy Shermans through frontal armor, while Sherman guns at the same range could not reliably penetrate Panther frontal armor. This enormous advantage in effective engagement range gave Panthers the theoretical capability to destroy enemy tanks before coming under effective return fire, the fundamental principle of German tank gunnery doctrine. The Maybach HL230P 30 engine represented sophisticated German automotive engineering applied to military requirements. This water-cooled 12-cylinder gasoline engine, mounted in a 60-degree V configuration, displaced 23.1 liters and weighed 1,200 kilograms. Maximum output of 700 metric horsepower, equivalent to 690 imperial horsepower, occurred at 3,000 revolutions per minute. Normal operational output was 600 metric horsepower at 2,500 revolutions per minute to reduce wear and extend engine life. This power output provided a power-to-weight ratio of 15.6 horsepower per ton, comparable to medium tanks of similar weight. The engine consumed high-octane gasoline, requiring 74-octane minimum for reliable operation, a fuel grade that Germany struggled to produce in adequate quantities from synthetic fuel plants as the war progressed. The AK-7-200 transmission represented advanced engineering that provided capabilities exceeding most contemporary designs. 7 forward speeds allowed optimal engine speed selection for various terrain and tactical conditions. 1 reverse speed provided retreat capability, though reverse speed was limited compared to forward speeds. The transmission was designed to handle the power output of the Maybach engine under normal operating conditions. However, the 45-ton combat weight exceeded design parameters, placing stress on transmission components that contributed to premature failures. Transmission oil overheating was a persistent problem, particularly during extended cross-country movement or combat operations, requiring frequent speed changes and high power output. Oil cooling systems proved inadequate for sustained high-stress operation, leading to thermal breakdown of lubrication and rapid wear of internal components. Maximum road speed of 46 km per hour provided tactical mobility comparable to other medium tanks. Cross-country speed of approximately 25 km per hour under favorable conditions gave the Panther adequate mobility for exploitation operations, when mechanical reliability permitted sustained movement. Operational range of 260 km on roads assumed optimal conditions with proper maintenance and careful fuel management. Cross-country range of approximately 100 km reflected the dramatically increased fuel consumption and mechanical stress of off-road movement. Fuel capacity of 730 litres required frequent refueling during sustained operations, creating logistics demands that German supply systems struggled to meet. Road fuel consumption of 2.8 litres per kilometre meant that a 100-kilometre road march consumed 380 litres, requiring more than half the fuel capacity. Cross-country consumption of 7.3 litres per kilometre meant that cross-country movement consumed the entire fuel load in approximately 100 kilometres, exactly matching the specified cross-country range. These specifications made the Panther theoretically superior to any Allied tank in service. The sloped frontal armour could defeat hits from American 75mm guns at all practical combat ranges. The long-barreled 75mm gun could destroy Sherman tanks at ranges exceeding 2,000 metres, far beyond the effective range of Sherman return fire. British armour commanders in Normandy would describe the Panther as the finest tank in the European theatre based purely on armour and firepower. German propaganda celebrated the Panther as proof of Aryan technical superiority, a weapon that would restore German dominance on the Eastern Front and repel the inevitable Allied invasion in the West. The reality revealed itself immediately at Kursk in the largest tank battle in history. German official reports documented the collapse with mathematical precision that shocked German military leadership and validated Soviet claims that German propaganda had dismissed as exaggeration. On July 5, 1943, 184 Panthers were operational from the 200 issued to Panther Regiment von Laukert between June 23 and June 29. The regiment had spent the intervening week conducting final preparations, minor repairs, and crew training on the new vehicles. Morale was high despite concerns expressed by experienced maintenance officers who recognized that the Panthers had not undergone adequate durability testing. Tank commanders who had fought in earlier Panzer III and Panzer IV tanks praised the Panthers' superior armor and firepower, believing these advantages would prove decisive in the coming offensive. The first day of combat revealed problems immediately. By July 7th, after just 2 days of combat operations, only 40 Panthers remained operational. This catastrophic 65% loss rate occurred primarily from mechanical breakdown rather than enemy action. Final drives failed under the stress of cross-country movement through muddy terrain. Transmissions overheated and seized. Engines caught fire from fuel system problems. Cooling systems leaked, causing engine overheating that led to catastrophic failures. Tracks broke under the strain of the 45-ton combat weight. Suspension components fractured from terrain, impacts that lighter tanks would have absorbed without damage. German maintenance units, overwhelmed by the volume of failures and lacking adequate spare parts, could not repair disabled Panthers fast enough to maintain operational strength. The German report dated July 20, 1943, compiled after the offensive had clearly failed, confirmed the extent of the disaster with bureaucratic precision. 41 Panthers remained operational. 85 were repairable by regimental level, maintenance if spare parts and time were available. 16 required repair in Germany because damage exceeded field maintenance capability. 56 had burnt out from enemy action. 2 had been destroyed by motor fires unrelated to combat. The operational rate at end of July was 16%, a figure so catastrophic that it triggered immediate investigations into what had gone wrong. Hitler personally demanded explanations, leading to investigations that blamed inadequate testing schedules rather than the fundamental design contradictions that actually caused the failures. The pattern established at Kursk repeated across every theatre where Panthers deployed throughout the war. Operational availability rates, the percentage of tanks actually available for combat on any given day rather than undergoing maintenance or awaiting spare parts, averaged between 35 and 40% throughout 1943. German records compiled after the war show 37% average availability at end of 1943 across all theatres. This meant that a Panther battalion nominally equipped with 96 tanks could expect approximately 35 tanks actually operational on any given day. The remaining 61 tanks were either undergoing maintenance, awaiting spare parts, awaiting transport to repair facilities, or disabled in forward areas awaiting recovery. This availability rate made sustained offensive operations impossible because operational strength declined throughout any extended operation, as mechanical failures accumulated faster than repairs could be completed. While these rates improved somewhat in 1944 to approximately 54% average, Panthers never achieved the reliability necessary for sustained offensive operations that German doctrine required. Some periods showed better performance that reflected improved crew training and established supply chains, rather than fundamental design improvements. September 1944 Eastern Front records indicate 75.8% availability, 552, operational of 728 total. The Battle of the Bulge in December 1944 showed 71.3% availability, 336 operational of 471 total. These improved figures, while better than earlier performance, still fell short of the 80 to 90% availability rates necessary for sustained offensive operations according to German pre-war planning assumptions. More importantly, these higher availability rates required extensive preparation, well-stocked supply depots, and favorable conditions that became increasingly rare as Allied pressure intensified and German logistics collapsed. The comparison with Sherman operational availability reveals the cumulative impact of reliability differences. While precise documentary confirmation of Sherman's 70 to 80% availability has not been located in all accessible sources, multiple authoritative analyses describe the Sherman as having superior reliability and superior mechanical reliability compared to the Panther. The operational reality visible in unit after action reports and divisional strength summaries consistently shows American armored divisions fielding higher percentages of their authorized tank strength than German panzer divisions throughout 1944 and 1945. This availability differential, approximately 30 to 45 percentage points favoring American forces, compounded the already substantial American advantage in total production numbers to create battlefield superiority that German tactical skill and technical specifications could not overcome. The core problem lay in a fundamental design contradiction. The Panther was conceived as a 35-ton medium tank, but the addition of heavy armor and a powerful gun increased combat weight to 45 tons, a 28% overload. This weight exceeded the design parameters of virtually every mechanical component, creating cascading reliability problems that no amount of field modification could fully solve. The most catastrophic failure point was the final drive, the mechanism that transferred power from the transmission to the drive sprockets that moved the tracks. The French army provided the most comprehensive post-war analysis of Panther reliability. France operated a full battalion of 50 Panthers through 1947 as part of the 503rd Tank Regiment, giving French forces almost twice as much operational time with Panthers as any German formation had achieved during the war. The official French Ministry of War report, titled Le Panther, published in 1947, stated explicitly that the truly weak spot of the Panther is its final drive, which is of too weak a design and has an average fatigue life of only 150 kilometers. French examination of abandoned Panthers found in Normandy in 1944 revealed that half showed evidence of final drive breaks. This was not combat damage but mechanical failure from normal operation. The metallurgical analysis conducted by French and American technical teams after the war revealed the underlying cause. German steel production in 1944 reached 28.5 million tons through incorporation of conquered territories including French Alsace-Lorraine, Polish Upper Silesia, and Czech Sudetenland. Production had peaked at 34.6 million tons in 1943. However, Germany had lost access to critical alloying metals necessary for high-quality steel production. Allied bombing of the Narben molybdenum mine in Norway in 1943 eliminated Germany's primary source of this critical element. Molybdenum increases steel's resistance to heat and fatigue. Nickel, another critical alloying element, became increasingly scarce as the war progressed, and Germany lost access to international markets. Soviet technical trials of captured Panthers found armor plates containing between 0.6 and 1.7% nickel in various locations. German sources described final drives as made of low-grade steel with low core strength of material used. While the specific percentages of deficiency could not be verified in all accessible primary sources, the general material degradation is extensively documented. The combination of design overload and material quality decline created a catastrophic reliability problem. Final drives that should have lasted thousands of kilometers under normal conditions failed after as little as 150 kilometers of operation. Transmission failures, engine problems, and suspension damage occurred at rates far exceeding those of Allied tanks. The production statistics tell the story of Germany's strategic error. Germany produced approximately 6,000 Panthers between January 1943 and April 1945. The breakdown by variant shows 842 AUS-FD from January to September 1943, 2,200 AUS-FA from August 1943 to August 1944, approximately 2,961 AUS-FG from March 1944 to April 1945, plus 329 Befehlspanzer command variants. Peak frontline strength reached 2,304 tanks on September 1, 1944. Production cost per Panther was 117,100 Reichsmarks without armament and radio, compared to 250,800 Reichsmarks for the Tiger I and 103,462 Reichsmarks for the Panzer IV. The United States produced 49,324 Sherman tanks in 11 plants between February 1942 and July 1945, representing the most successful tank production program in military history, measured by total units produced and sustained over time. The Sherman, officially designated M4 medium tank, evolved through multiple variants using different engines, transmissions, and hull configurations while maintaining commonality of critical components that simplified logistics and maintenance. The most common variant used the Continental R975 radial engine producing 400 horsepower, licensed from the Wright R975 Whirlwind aircraft engine. This 9-cylinder air-cooled radial engine, originally designed for aircraft, proved remarkably reliable in tank application, despite initial skepticism about adapting aircraft engines to ground vehicles. The Sherman weighed 30 metric tons in combat configuration, 15 tons lighter than the Panther. This lower weight reduced stress on all mechanical components, improving reliability and extending service life. The main armament on most Shermans was a 75mm M3 gun, a competent weapon adequate for destroying most Axis tanks through 1943, but increasingly inadequate against heavily armoured German tanks like the Panther and Tiger from 1944 onward. Maximum armour of 76mm on the frontal hull, mounted vertically rather than sloped, provided less protection than Panther armour but proved adequate against most German tank guns at medium ranges. Maximum road speed of 40 km per hour, slightly slower than the Panther, provided adequate tactical mobility for American armoured doctrine that emphasized sustained operations over maximum speed. The Sherman's true superiority lay not in specifications but in reliability, maintainability, and production efficiency. The Continental R975 engine required minimal maintenance compared to the complex Maybach engine in the Panther. Oil changes every 250 hours of operation versus every 100 hours for the Panther reduced maintenance burden. Air cooling eliminated the complex cooling system that plagued Panther operations, removing an entire category of potential failures. The transmission, though less sophisticated than the Panther's 7-speed design, proved remarkably reliable and could be replaced in field conditions within 8 hours by trained maintenance crews. Final drives, conservatively designed with adequate strength margins, rarely failed under normal operating conditions. Suspension components using vertical volute spring bogies instead of interleaved road wheels could be maintained and repaired quickly without extensive disassembly. Production efficiency gave the Sherman overwhelming numerical advantages. The average Sherman required approximately 10,000 man-hours to produce in established factories, operating at peak efficiency by 1944. The Panther required approximately 15,000 man-hours, 50% more labor for each unit. American factories used advanced production techniques, including extensive subassembly, standardized components across variants, and progressive assembly methods that minimized skilled labor requirements. German factories relied more heavily on skilled craftsmen to fit components that were less precisely standardized, increasing production time and costs. American production peaked at over 2,000 Shermans per month during mid-1944. German Panther production peaked at approximately 380 units per month, less than one-fifth American output, despite Germany dedicating proportionally more industrial capacity to tank production. The operational consequences of these production differentials compounded over time. American armored divisions that suffered tank losses in combat received replacement vehicles within weeks, sometimes within days if supply lines were functioning normally. Crews knew that destroyed tanks would be replaced, reducing psychological stress and encouraging aggressive tactics. German panzer divisions that suffered losses waited months for replacements if they received any at all. Crews knew their Panthers were irreplaceable, creating caution that undermined German tactical doctrine requiring aggressive action. By late 1944, many German panzer divisions operated at less than 50% authorized tank strength, not from combat losses alone, but from inability to replace losses at rates matching attrition. Yet the Sherman won the war while the Panther lost it, because specifications written on paper matter less than availability on the battlefield. The fundamental principle that determined victory was not which tank had better armor or firepower, but which tank was actually present and operational when needed. The Sherman achieved operational availability rates between 70 and 80% throughout the war, though direct documentary confirmation of this precise figure has not been located in accessible sources. Multiple authoritative sources describe the Sherman as having superior reliability and superior mechanical reliability compared to the Panther. The operational availability differential, approximately 30 to 45 percentage points in favor of the Sherman, meant that American armored divisions consistently fielded far more operational tanks than German panzer divisions, despite comparable nominal strength. The maintenance burden imposed by the Panther consumed resources Germany could ill afford. Each Panther battalion required specialized recovery vehicles, mobile workshops, and stocks of spare parts that dwarfed the logistics footprint of a Sherman battalion. A typical American armored division required approximately 200 trucks dedicated to armored vehicle maintenance and supply. A German Panzer division equipped with Panthers required approximately 400 trucks for the same function, trucks that Germany did not possess in sufficient quantities and could not fuel even if possessed. The fuel consumption differential compounded the problem. A Sherman battalion conducting a 100-kilometer road march consumed approximately 14,000 litres of gasoline. A Panther battalion conducting the same march consumed approximately 35,000 litres, assuming all vehicles completed the march without mechanical failure, which historical records suggest was unlikely. By late 1944, Germany was producing approximately 6 million tons of synthetic fuel annually, barely 1/10 of American petroleum production. The psychological impact on German forces of their supposedly superior equipment's mechanical fragility emerges clearly from captured documents and post-war interviews. German tankers learned through experience that their Panthers were unreliable. The knowledge that their vehicle might break down at any moment, stranding them deep in enemy territory far from recovery assets, created caution that undermined the aggressive exploitation of tactical success that German doctrine required. Commanders hesitated to commit Panthers to bold maneuvers because they feared mechanical failure more than enemy fire. This psychological burden, imposed by flawed engineering, contributed to German tactical paralysis during the final year of the war. The Battle of the Bulge in December 1944 demonstrated these problems at operational scale. German forces committed 471 Panthers to the offensive, with 336 operational at start, a 71% availability rate that represented exceptional preparation. Within 1 week, mechanical failures had reduced operational strength by approximately 1/3, not from combat losses but from breakdowns on the advance. Panthers abandoned for mechanical reasons littered the roads through the Ardennes. German recovery units, already stretched thin, could not retrieve all disabled vehicles before American forces recaptured the territory. The offensive failed not primarily from lack of fuel, as popular accounts suggest, but from the systemic unreliability of German armoured vehicles that limited operational tempo even when fuel was available. The contrast between German and American approaches to military technology extended beyond tanks to virtually every category of equipment. German small arms were magnificently engineered but expensive and slow to produce. The MP-40 submachine gun required approximately 10 hours of skilled machinist time to manufacture. The American M3 grease gun required less than 3 hours of semi-skilled labor. Both weapons fired the same caliber ammunition at similar rates. The American weapon was uglier, cruder, and vastly more practical for mass production. This pattern repeated across artillery, aircraft, vehicles, and every category where American pragmatism confronted German perfectionism. The philosophical difference reflected fundamentally different understandings of modern industrial warfare. German military culture, rooted in Prussian traditions emphasizing individual excellence and technical sophistication, could not adapt to the reality that 20th-century warfare rewarded mass production over individual perfection. The German army entered World War II with doctrines developed from World War I experience, emphasizing breakthrough and exploitation through concentrated armored formations, employing technically superior equipment operated by highly trained elite forces. This doctrine achieved spectacular successes in Poland and France against enemies who were unprepared and poorly organized. Against the Soviet Union and the United States, nations capable of absorbing initial defeats and mobilizing vast industrial resources, the German approach failed catastrophically. American military doctrine, informed by different historical experience and different industrial capacity, embraced mass production and logistical sustainability as primary virtues. The Sherman tank exemplified this philosophy. It was not the best tank by any specification. It was the best tank that American industry could produce in sufficient quantity, that American logistics could support in global operations, that minimally trained crews could operate effectively, and that field maintenance units could keep operational under combat conditions. These virtues, dismissed by German engineers as evidence of technical inferiority, proved decisive. The final accounting reveals the magnitude of Germany's strategic error. 6,000 Panthers, hamstrung by mechanical unreliability, achieved operational effectiveness, roughly equivalent to 3,000 reliable tanks. The resources consumed by Panther production could have produced approximately 9,000 Panzer IV tanks. The Panzer IV, while inferior to the Panther in specifications, was mechanically reliable and adequate for combat against all but the heaviest Allied armour. 9,000 Panzer IVs, actually available for combat rather than awaiting maintenance, would have provided far greater military value than 6,000 temperamental Panthers. This conclusion is not speculation but mathematical certainty derived from operational availability statistics and production cost analysis. The human cost of German over-engineering extended beyond logistics to training and doctrine. Panther crews required extensive specialized training to operate and maintain their complex machines. This training took months that Germany increasingly could not afford. Sherman crews could be trained to basic proficiency in weeks, and the mechanical simplicity of the Sherman meant that crew survivability was higher because catastrophic mechanical failures were less likely to trap crews in disabled vehicles under fire. German tank crew casualties from mechanical failures that prevented escape from damaged vehicles were proportionally higher than American casualties from the same cause, though precise comparative statistics are difficult to establish from available records. The British Army's experience with captured Panthers provided additional confirmation of German reliability problems. British forces tested Panther No. 433, a mid-production Ausf, a variant, in mobility trials in the United Kingdom during 1944. The British technical description of this specific tank was completed in late May 1944. British reports confirmed German findings about final drive weakness and noted additional problems with the interleaved road wheel suspension that German designers had implemented to improve cross-country performance. The overlapping wheel design, featuring wheels mounted on overlapping axles rather than individual bogies, provided superior weight distribution and ground pressure reduction. This allowed the Panther to traverse soft ground more effectively than tanks using conventional suspension designs. The theoretical advantages were genuine and measurable in controlled testing conditions. The practical reality under combat conditions told a different story. Mud accumulated between the overlapping wheels during cross-country movement. In winter conditions, common across much of the Eastern Front and Northern Europe, this mud froze solid overnight. By morning, the suspension was locked, immobilizing the tank until crews could chip away the ice or wait for temperatures to rise sufficiently for melting. This process could take hours under favorable conditions, days under severe winter weather. German tankers in Russia learned to avoid muddy terrain whenever possible, limiting their tactical flexibility to avoid suspension immobilization. Maintenance requirements for the interleaved suspension exceeded those of conventional designs by an order of cos. Magnitude. Changing an outer road wheel on a Sherman required approximately 30 minutes with proper tools. Changing an inner road wheel on a Panther required removing up to 8 outer wheels first, a process that could consume an entire day even with experienced maintenance crews and proper equipment. Under field conditions, with improvised tools and time pressure from tactical situations, this maintenance burden became prohibitive. German maintenance units, already overwhelmed by final drive replacements and transmission repairs, faced additional workload from suspension maintenance that conventional designs would have avoided. British armour officers, after extensive evaluation of captured Panthers, concluded that despite superior armour and firepower, the Panther's mechanical complexity made it unsuitable for British operational requirements. British tank doctrine emphasised reliability and maintainability precisely because British military planners understood that operational availability determined battlefield effectiveness more than individual technical specifications. The production timeline for Panthers revealed additional strategic failures in German planning. Hitler personally intervened in Panther development multiple times, demanding increased armour protection and more powerful armament, while simultaneously demanding accelerated production schedules. These contradictory requirements created exactly the problems that materialized at Kursk. The Panther was rushed into production before adequate testing could identify and resolve the final drive weakness. Normal vehicle development includes extensive durability testing, where prototypes are subjected to conditions exceeding expected operational use to identify failure points before mass production begins. The Panther program, compressed by Hitler's demands, skipped or abbreviated these crucial testing phases. The result was a weapon system that failed catastrophically when exposed to actual combat conditions, exactly the outcome that proper testing would have prevented. The organizational culture within the German military-industrial complex compounded these problems. German engineering culture emphasized technical excellence and sophisticated solutions to complex problems. This culture produced genuine innovations, including the first operational jet fighter, the first ballistic missiles, advanced submarine designs, and numerous other technological achievements. However, this same culture struggled with the practical requirements of mass production and field maintenance. German engineers designed weapons for ideal conditions, assuming proper maintenance by trained technicians using specialized tools in well-equipped facilities. American engineers designed weapons for realistic conditions, assuming field maintenance by minimally trained personnel using improvised tools under combat stress. These different design philosophies produced the Sherman and the Panther, two tanks that embodied opposite approaches to military engineering. The training burden imposed by Panther complexity extended beyond crews to include maintenance personnel at every level. A Sherman battalion required approximately 40 maintenance personnel with basic mechanical skills. A Panther battalion required approximately 80 maintenance personnel, including specialists trained in complex transmissions, specialized final drive procedures, and sophisticated engine maintenance. Germany could not produce these trained specialists fast enough to meet demand. By late 1944, Panther battalions routinely operated with maintenance units at 50 to 60% of authorized strength, further reducing operational availability. Untrained or minimally trained mechanics attempting complex repairs resulted in additional damage, creating cascading maintenance problems that reduced availability even further. The fuel logistics challenge created by the Panther cannot be overstated. The Panther cannot be overstated. 2.8 liters per kilometer road consumption, while accurately stated in specifications, assumed optimal conditions with properly maintained engines and transmissions. Actual field consumption often exceeded 3 liters per kilometer due to mechanical problems that reduced efficiency. A Panther, traveling from Germany to the Eastern Front, consumed its entire fuel load multiple times during the journey. Germany lacked sufficient fuel trucks to support large-scale Panther deployments. Panzer divisions were frequently immobilized, not by enemy action but by inability to deliver fuel to forward units. The strategic impact of this fuel shortage shaped German defensive strategy during 1944. German commanders knew their Panthers could not sustain mobile operations because fuel supply could not support sustained movement. This knowledge forced defensive tactics that surrendered initiative to Allied forces, exactly the opposite of German doctrine that required aggressive maneuver and exploitation. American forces captured their first Panthers in Tunisia during May 1943, though in limited numbers. The systematic capture of Panthers in operational condition occurred primarily during the Normandy campaign, beginning June 1944. American ordnance units established enemy equipment evaluation teams attached to field armies specifically to identify, recover, and analyze captured German vehicles. These teams included mechanical engineers, metallurgists, and intelligence specialists trained to extract maximum information from captured equipment. The intelligence gathered from these teams informed tactical bulletins distributed throughout American forces, providing tank crews and infantry units with specific information about Panther vulnerabilities and recommended engagement tactics. American forces captured multiple Panthers in France and Germany during 1944 and 1945, with systematic recovery and analysis procedures that evolved throughout the campaign. It is believed that 14 captured Panthers were shipped to the United States for technical evaluation, though definitive shipping records have not been located in accessible archives. Most captured Panthers were scrapped after testing, with only 5 Panthers surviving in America today as museum pieces. Aberdeen Proving Ground in Maryland tested captured German vehicles during World War II, with documentation confirming that for more than a year, captured enemy vehicles had been arriving at the facility by January 1944. Panthers were eventually displayed at Aberdeen's Ordnance Museum collection, confirming United States possession and testing of multiple examples. However, specific technical reports from Aberdeen detailing 1944 Panther test procedures and results have not been located in fully accessible archives, leaving details of specific test protocols unclear from available documentation. The intelligence analysis of Panther capabilities and weaknesses influenced American tactical doctrine throughout the final 18 months of the war in Europe. Understanding that the Panther's 75mm gun could destroy Sherman's at ranges exceeding 2,000 meters, while Sherman's 75mm guns could not reliably penetrate Panther frontal armor at any range, American doctrine emphasized tactics that exploited Panther weaknesses rather than confronting its strengths. Tank destroyer doctrine, built around the 3-inch gun mounted on M10 Wolverines, and later the 90mm gun on M36 Jackson tank destroyers, provided the primary anti-Panther capability. These vehicles, more lightly armored than tanks but mounting more powerful guns, were positioned in defensive positions where they could engage Panthers at extended ranges or from ambush positions targeting vulnerable side armor. Infantry anti-tank tactics evolved rapidly as American forces gained experience fighting Panthers. The 2.36-inch bazooka, effective against earlier German tanks, proved inadequate against Panther armor. Tactical bulletins distributed to infantry units emphasized that bazookas should target side and rear armor at close range, not frontal armor. Infantry units learned to allow Panthers to pass their positions, then engage from behind where armor was thinnest and ammunition stowage was vulnerable. Close assault tactics using satchel charges and sticky bombs required courage bordering on recklessness but proved effective when properly executed. American infantry casualties from Panther engagements remained high throughout the war, but the kill ratio improved steadily as troops learned and applied effective tactics distributed through training and tactical intelligence bulletins. Artillery became the most effective American counter to Panthers, not through direct fire, but through indirect fire and mobility denial. Forward observers learned to call artillery fire on disabled Panthers that German recovery units could not immediately retrieve. American artillery doctrine emphasized rapid response to fire missions, with battalion-level artillery capable of delivering concentrated fire within 5 minutes of observer request. Panthers disabled by mechanical failure, immobilized by terrain obstacles, or simply stopped to engage American forces, became targets for artillery concentrations that destroyed tanks or forced crews to abandon vehicles. The psychological effect on German tankers was significant. Panther commanders learned that stopping for any reason invited artillery fire that their armor could not protect against. This knowledge created pressure to keep moving, exactly the operational tempo that Panther mechanical reliability could not sustain. Air power provided additional capability against Panthers, though direct air-to-ground attacks on individual tanks proved less effective than popular accounts suggest. Tactical aircraft armed with rockets and bombs achieved modest success rates against moving tanks. The primary value of air power against armored forces was interdiction, attacking supply columns, fuel trucks, repair facilities, and other supporting infrastructure that sustained Panther operations. A Panther without fuel, spare parts, or recovery capability was as useless as a destroyed Panther. American air superiority over European battlefields by mid-1944 meant that German armored forces moved primarily at night to avoid air attack, further straining mechanical reliability and complicating logistics. The cumulative effect of air interdiction on German armored operations exceeded the direct destruction of tanks through ground attack. The systematic intelligence analysis conducted by American and British technical teams examining captured Panthers produced detailed reports that were distributed through intelligence channels to commanders at division and corps level. These reports included specific technical specifications, armor thickness measurements from multiple angles, penetration data for various weapons at various ranges, photographs of vulnerable points, and recommended engagement tactics. Company-level officers received simplified tactical bulletins highlighting key vulnerabilities and recommended techniques. This intelligence distribution system, mundane and unglamorous compared to dramatic battlefield actions, shaped tactical decisions that saved American lives and accelerated German defeat. The value of this intelligence work is difficult to quantify precisely, but emerges clearly from after-action reports that document how American units modified tactics based on distributed intelligence about German equipment capabilities and vulnerabilities. The broader strategic lesson from Panther development and deployment extends beyond World War II to shape American defense procurement for decades. The principle that the best weapon system is the one that is actually available when needed, rather than the one with the most impressive specifications, became foundational to American military planning after World War II. This philosophy directly contradicted the approach that had dominated military procurement in the 1930s, when specifications emphasized theoretical maximum performance with less attention to reliability and maintainability. The Panther's failure, analyzed in detail by post-war studies, validated the alternative philosophy that adequate performance sustained over extended operations defeats superior performance that cannot be maintained under field conditions. This principle informed development of every major American armored vehicle designed after World War II. The M48 Patton tank, entering service in 1952, emphasized mechanical reliability and ease of maintenance as primary design requirements equal to armor and firepower. Lessons learned from Panther analysis influenced transmission design, final drive engineering, suspension systems, and maintenance accessibility. The M60 tank, entering service in 1960, continued this emphasis on reliability and maintainability. The M1 Abrams tank, entering service in 1980, represents the culmination of this philosophy. While incorporating sophisticated technology, including composite armor and a gas turbine engine, the Abrams was designed from the beginning with reliability, maintainability, and logistical sustainability as requirements co-equal with combat performance. This represented the direct rejection of the German approach that had prioritized individual technical superiority over systemic sustainability. The institutional changes within American military procurement following World War II reflected hard-won lessons about the relationship between technical specifications and operational effectiveness. Durability testing became mandatory for all new weapon systems, with prototypes subjected to conditions exceeding expected operational use before production approval. Maintenance procedures were evaluated as rigorously as combat performance. Logistics requirements were calculated and evaluated before production decisions. Supply chain sustainability became a procurement criterion. These changes, revolutionary at the time, are now so thoroughly integrated into military procurement that their origin in World War II, lessons about German over-engineering, has been largely forgotten. The Panther's failure created the framework for successful American weapon development that continues to present day. Universities teaching courses in engineering management continue to use the Panther as a case study in how not to develop complex systems. The case study examines requirements creep, the process by which additional capabilities are added during development without proportionally increasing the design parameters of supporting subsystems. Business school students study the Panther as an example of how an organization's cultural values can undermine effective decision-making. German military culture valued technical sophistication and engineering excellence, leading to design decisions that produced sophisticated systems unsuited to the operational environment. American military culture valued pragmatism and results, leading to design decisions that produced crude but effective systems suited to sustained operations. Neither culture was objectively superior, but American culture proved better adapted to industrial warfare's requirements. The lesson extends beyond military applications into any domain where reliability, maintainability, and sustainability matter as much as raw performance. The comparative analysis of German and American tank production reveals the mathematical inevitability of German defeat once both nations committed to total industrial mobilization. Germany's decision to produce 6,000 complex Panthers rather than 9,000 simpler Panzer IVs represents the kind of strategic error that compounds across an entire military-industrial system. Similar errors occurred in aircraft production, where Germany produced sophisticated fighters requiring extensive maintenance rather than adequate fighters in greater numbers. Artillery production emphasized precision and range at the expense of quantity. Small arms production emphasized quality over manufacturability. Across every category of military equipment, German industry made choices that optimized individual weapon performance while undermining collective force capability. American industry made the opposite choice consistently. The Sherman was adequate, not excellent. The P-51 Mustang fighter was effective, not revolutionary. The M1 Garand rifle was reliable, not perfect. American artillery emphasized rapid production and ammunition abundance over maximum range. This systematic preference for adequacy sustained over time proved decisive. By 1944, American forces could afford to lose equipment at rates that would have crippled German forces because American production replaced losses within weeks while German losses accumulated. American maintenance units could repair damaged equipment quickly because designs emphasized maintainability. American supply chains delivered spare parts, fuel, and ammunition reliably because logistics planning began during weapon design rather than after deployment. These advantages, individually modest, compounded across millions of pieces of equipment and years of sustained operations to create overwhelming superiority. The Panther today represents a fascinating historical paradox that extends beyond simple technical analysis to encompass fundamental questions of culture, doctrine, strategic decision-making, and the nature of modern warfare. It was simultaneously one of the best tanks of World War II in terms of armor protection and firepower, and one of the worst in terms of reliability and operational sustainability. It was a triumph of engineering sophistication that demonstrated German technical capabilities at their peak, and simultaneously a disaster of strategic planning that demonstrated the catastrophic consequences of divorcing technical excellence from operational reality. It impressed everyone who saw it, intimidated Allied tankers who faced it in combat, earned respect from enemy armor, officers who evaluated captured examples, and yet disappointed everyone who tried to maintain it under actual combat conditions, far from rear area maintenance facilities with adequate tools and spare parts. The Panther was exactly what Germany did not need at the moment Germany needed it most. Germany needed adequate tanks in overwhelming numbers to replace catastrophic losses on the Eastern Front and prepare for inevitable Allied invasion in the West. Germany produced sophisticated tanks in inadequate numbers that spent more time undergoing maintenance than engaging enemies. Germany needed simple, reliable vehicles that minimally trained crews could operate and field maintenance units could repair. Germany produced complex vehicles requiring extensive crew training and specialized maintenance that consumed disproportionate resources. Germany needed weapons optimized for defensive warfare that could be produced despite shrinking industrial capacity and material shortages. Germany produced weapons optimized for offensive warfare that required vast industrial resources and materials that were no longer available in adequate quantities or quality. These contradictions emerged from German military culture, strategic assumptions, and decision-making processes that proved fundamentally unsuited to the kind of war Germany was fighting by 1943. German military tradition emphasized quality over quantity, technical sophistication over simplicity, and individual excellence over mass production. These values had served Prussia and Germany well in previous conflicts where wars were decided by relatively small professional armies fighting decisive campaigns of short duration. World War II was not that kind of war. It was a war of industrial attrition where victory required sustained production over years, where lost equipment and personnel needed rapid replacement, where logistics determined what was possible more than tactics, where systemic sustainability mattered more than individual superiority. American military culture, shaped by different history and different strategic circumstances, proved better adapted to industrial warfare's requirements. American tradition emphasized practicality over perfectionism, results over elegance, and mass production over craftsmanship. The American military was not inherently superior to the German military in training, doctrine, or tactical skill. American advantages lay in industrial capacity, logistics, and philosophical approach to weapon development that prioritized adequacy sustained over time, rather than excellence that could not be maintained. These advantages, individually modest, compounded across millions of pieces of equipment and years of sustained operations to create overwhelming superiority that German technical excellence could not overcome. The legacy of the Panther extends to the present day in ways both obvious and subtle that continue to influence military planning, engineering education, and defense procurement policy. Every American armored vehicle designed since World War II incorporates lessons learned from systematic analysis of captured German tanks. The emphasis on reliability over raw performance, the focus on maintainability and logistical sustainability, the understanding that the best weapon system is the one that is actually available when needed rather than the one with the most impressive specifications. All these principles trace back to intelligence analysis conducted during and immediately after World War II. These lessons, purchased at terrible cost in American and Allied lives, saved countless additional lives in subsequent conflicts where reliable equipment proved decisive. The Panther serves as permanent reminder to military planners and defense procurement officials that engineering excellence divorced from operational reality creates weapons that lose wars despite winning individual battles. It stands as testament to the principle that in modern industrial warfare, systemic sustainability defeats individual superiority when sustained over extended operations. The tank that looks magnificent in the museum, that impresses visitors with its massive armor and powerful gun, lost to the tank that worked reliably in the mud, that mechanics could repair quickly under field conditions, that was actually present when battle was joined. These lessons remain relevant to contemporary defense planning where technological sophistication must be balanced against reliability, maintainability, production feasibility, and logistical sustainability. Modern engineering students studying the Panther learn about requirements creep, the dangerous process by which additional capabilities are added during development without proportionally increasing the design parameters of supporting subsystems. They learn about the importance of durability testing before production commitment. They learn about the relationship between design complexity and field maintainability. They learn that the most elegant solution to an engineering problem is not necessarily the best solution when operational constraints are considered. These lessons extend beyond military applications into commercial product development, infrastructure engineering, and any domain where reliability matters as much as capability. Modern military planners studying the Panther learn about the dangers of cultural biases influencing technical decisions. They learn about the importance of aligning weapon characteristics with actual, strategic requirements rather than idealized visions of how wars should be fought. They learn about the cumulative impact of seemingly modest reliability differences when compounded across thousands of vehicles and months of sustained operations. They learn that operational availability rates matter more than nominal strength. They learn that logistics determines what is possible more than tactics or technology. These lessons inform contemporary debates about defense spending, procurement priorities, and force structure decisions. The mathematical analysis of Panther performance reveals truths that narrative accounts sometimes obscure. 49,000 Shermans at 75% availability provided approximately 36,750 tanks actually in combat at any given time. 6,000 Panthers at 40% availability provided approximately 2,400 tanks actually in combat at any given time. The 15-to-1 numerical advantage in actual battlefield presence overwhelmed the Panther's technical superiority in individual engagements. German forces could win individual tank battles through superior armor and firepower and still lose campaigns, lose theaters, lose the war, because they could not sustain operations at the tempo required for victory. Superior specifications on paper could not compensate for systemic failure to deliver operational capability when and where needed, for as long as needed. The Panther's magnificent failure teaches more than its spectacular specifications ever could, precisely because failure reveals truth that success often obscures. Success can be attributed to many factors and allows multiple interpretations. Failure, particularly catastrophic failure of sophisticated systems, reveals fundamental problems that cannot be rationalized or attributed to bad luck. The Panther failed because German strategic assumptions, technical culture, and procurement processes produced a weapon unsuited to Germany's actual strategic situation in 1943. That failure, documented in meticulous detail by German military bureaucracy and analyzed systematically by Allied intelligence, provides lessons of enduring value about the relationship between technical excellence and military effectiveness.